First off, what even is a base? They're defined as a set of digits used to represent numbers. For example, we live in a base 10 world because we have 10 fingers. If you think about it, all the numbers that we use on an everyday basis are built off of 10 digits, 0 through 9. So let's get straight into counting. How many cans of tuna can we see here? There's 12, which represents one full group of 10 and 2 left over. But what about Manny the monster? Manny has 6 fingers total, which means he counts in base 6, or in groups of 6. He'd say that there's 20 cans of tuna because he sees 2 full groups of 6, or 2 full hands with 0 left over. Okay, so now we know how Manny counts, even though it's probably much more different than what you're used to, but you'll get it eventually. Let's continue forward. How many tomatoes do you think Manny counts here? Pause the video and see if you can figure this out. If you said 45, you'd be correct. We can ration the tomatoes into 4 full groups of 6 and 5 left over. For future reference, remember to place the base number on the bottom right so we don't get confused on what base we're in. Okay, so let's introduce a new creature. Ophelia the ogre has 4 fingers total, so she can count in base 4. How many Tom Hollands can we count if we're in base 4? We have to go another place value representing one group of 16, or 4 groups of 4, because once we hit this threshold, we need a new place value, just like when we have 10 groups of 10 in our system. Then, we have 3 groups of 4 and 2 ones left over, so our final answer is 132. So now that we've had a lot of practice with bases, let's move on to a more juicy word problem. Gerald is a gremlin who counts in base 9. If he has 2,384 base 9 almonds, what does this mean in our world, or in base 10? How many almonds is this going to represent? Okay, as we always do, let's break up 2,384 into what we already know. On the right, we have 4 ones left over. This 8 represents 8 full groups of 9, and this 3 represents 3 full groups of 81, aka 9 groups of 9. Then, this 2 means 2 full groups of 729. When we expand all of this, we get 2 times 9 to the 3rd power, plus 3 times 9 to the 2nd power, plus 8 times 9 to the 1st power, and 4 times 9 to the 0th power. I'll write an equivalent expression right underneath it in case you're a little confused, and the final answer is 1,777. Great job! So even though we've made all of these ridiculous scenarios with these cool gremlins and anyways, these different bases actually exist in real life. For example, Babylonian was an ancient number system that utilized base 60. Look at how crazy that looks. You've also probably seen Roman numerals at many times in your life, which uses symbols for 1, 5, 50, 100, and so on. Also, if you use computers, know that computers use the binary number system, aka base 2. This means the only digits are 0 and 1, representing off or on. Now that you've encountered lots of practice with bases, you should be comfortable with converting between different ones. Next Monday, we'll explore even further by doing cool operations in different bases. Bye everyone!